Welcome back to Yijin Hardware CNC Analysis. This episode might help broaden your horizons and quickly improve your machining capabilities. In this analysis, we'll watch a video from Brother Machine Tools showcasing the rapid machining of an aerospace product in just 3 minutes and 25 seconds. The material used is 7-Dow-75 aluminum alloy. Let's take a look at how they achieve such fast machining. The machine used for this process is the Brother M200X3 milling and turning 5-axis composite machine. The advantage of Brother machines lies in their fast movement speeds and tool change times, only 0.8 seconds for tool changes. The spindle is a BT30 with a maximum speed of 10,000 RPM, widely used for medium and small batch products in the energy, aerospace, and medical fields. Like and subscribe. Let's dive into the analysis now. First, we can see that the fixture used is a self-centering vise, clamping at about 4 millimeters at the bottom, which provides maximum cutting space while ensuring clamping rigidity. They are currently using 40 millimeters high-performance aluminum to rough mill both sides of the product. In the lower left corner, we can see the cutting parameters: spindle speed of 10,000 RPM, feed rate of 4,500 millimeters per min, depth of cut of 4 millimeters, and width of cut of 27 millimeters. Calculating this gives a linear speed of 1,250 meters per minute, with a feed per tooth of 0.15 millimeters and a material removal rate of 500 cubic centimeters per minute. The machining efficiency is quite high. We can see that during programming, they chose to use climb milling instead of conventional milling. This method effectively reduces cutting resistance and protects the cutting edge, making it suitable for any material. Now, switching to roughing on the other side, you can see that the Brother machine is very quick in both C-axis rotation speed and tool change speed. When using a shoulder mill with a larger depth of cut, it's advisable to use climb milling rather than back and forth cutting. This approach helps ensure that the chip thickness gradually decreases during machining, allowing for higher feed rates and extending tool life. This is the fundamental reason we typically prefer climb milling over conventional milling. In climb milling, the chips produced gradually thin out, which reduces the stress applied to the cutting edge. In contrast, with conventional milling, the stress is applied explosively to the cutting edge at the moment of chip formation, leading to chipping or wear. This is a crucial theoretical concept, and we might create a dedicated video to explain the thinning chip effect in detail. After drilling, they switch to a 3-flute integrated carbide end mill. The machining parameters are shown in the lower left. Spindle speed remains at 10,000 RPM, feed rate is 3,000 millimeters per min, depth of cut is 5 millimeters, and width of cut is 10 millimeters, effectively a full cutter groove. These parameters can be significantly improved. The current material removal rate is only 150. The spindle's maximum speed limits the tool's performance, as this tool could easily handle 20,000 RPM. Even at 20,000 RPM, the linear speed would only reach around 600 ms per minute. Most of the material on the product side is removed using a grooving technique, which saves a lot of machining time. Then they flip the workpiece over for processing. The C-axis response speed is very fast, and this closed cavity is machined using a spiral downcutting method, a common machining technique. We can see that they're essentially using the full cutter to remove chips. After roughing, the cavity is directly finished. Now they're ready to cut the remaining material. This leftover material has some weight, and since the bottom is hollow, it will drop directly upon cutting rather than flying away. Now they switch to a diameter 12 end mill to finish each profile using the side edge. The linear speed remains constant, but the feed rate and width of cut are significantly reduced, leaving a 0.2 millimeter allowance for a clean finish. At this point, you'll notice that a lot of time is actually wasted on smaller tools, while roughing is relatively quick. So now it's the machine's performance, not the tool, that limits machining efficiency. If the spindle speed were increased to 20,000 RPM, the feed rate would double. Thus, when machining aluminum under good rigidity, machining parameters are the key factor affecting efficiency. After finishing, they begin drilling. The advantage of using carbide drill bits is their high rigidity, allowing them to drill directly without pre-drilling. Next comes the chamfering. We can see that the machine's linear axis moves very quickly and smoothly. After chamfering, the product is ready to be removed from the machine. Let's take a look at this product. It's looking pretty good. The bottom of the product has a row of marks left by the self-centering vise. Feel free to adjust any specific terms if necessary.